Hello everyone, welcome to another lecture of School of Solana. So in this lecture, we'll be talking about Solana programming model again. We'll do some form of recap of our previous lecture, and then we'll introduce the basics of PDAs, which are Program Derived Addresses. Please note that we'll only be talking about basics of PDAs, so PDAs are quite a complex topic, so if you're interested in learning more, there are many different sources where you can find different details about PDAs, and I do recommend you to reading that because this is a pretty important concept on Solana. We'll be also talking about SPO tokens and tokens repository. Program repository. We briefly introduced SPO tokens in our lecture number 1, but we'll be talking a little bit in detail about them today. So after we have this part of the lecture done, we'll move on to a hands-on example where we'll be implementing a simple Solana program with PDA. So let's do a little bit of recap. We talk about accounts. There are two different types of accounts on Solana. There are program accounts and data accounts. For program accounts, we're talking about accounts that are storing a bytecode of our program, which means these programs are executable by Solana runtime. All of these program accounts do not store any data. All of the programs on Solana are stateless. If we want to supply any data to our program, we need to use our data accounts. These data accounts are not executable and only store the data that we use as an input or we want to modify them from our program. Only the data account's owner can modify its data and subtract the LAMP ports that are currently in the account. To prevent the account from being deleted, we must pay some sort of rent, or we pay a certain amount of tokens to be set as a rent exempt. So keep in mind, this is something that we talked about in the previous lecture. There is a big distinction between program and data accounts. Another important part of our previous lectures were transactions. All of the basic operational unit on Solana are instructions. One or more instructions can be bundled into a transaction, and these instructions in one transaction are then processed in order and atomically. This is something similar to any databases in the world. So essentially we can form different instructions into one transactions, and if all of these instructions were executed successfully, then the transaction is complete. If one of these instructions fails, that means that the transaction is reverted. When we are defining these transactions, we must forward declare every account we intend to read from or write to. We also need to be aware of any potential security risks because obviously all of these transactions can be constructed by any user of Solana. So if we look at our instruction format, we have some program ID, we have all of the accounts we need to supply, and then some form of 8-bit data that we supply to the program. If we look at the accounts, we can specify different amount of accounts that we need in terms of our transactions. So if we need to have, for example, 5 different accounts in this case, we're specifying 5 or 6 different accounts. All of these accounts can be signed, not signed, writable, or also read-only. So now that we have described our basics, let's jump into a PDAs. PDAs can be quite hard to understand in the beginning, so I will only cover the basics and try to cover them in a way that it is easily understandable even to a complete beginner. So let's just talk about the motivation of creating PDAs or the motivation of whole concept of PDAs on Solana. Let's say we have 2 different users on our blockchain. We have user A and user B. Both of these users have wallets already created wallets, and both of them own private key to these wallets. So for example, if you have Phantom wallet ready in your browser, this wallet in your browser holds your private key that you can use to sign transactions on behalf of that particular wallet or that particular account. So let's just briefly look at it in detail. All of the wallets on Solana are owned by System Program. If we want to do some form of transactions from our wallet, we need to ask System Program to process this transaction or process this transfer function. And to do that, we ask System Program, and while asking the System Program, we also supply our private key. That tells the System Program that we are actually owner of that particular account, and we are able to do transactions and transfers on behalf of that wallet. So that means if we have two distinct users on our blockchain, both of them hold the private key, there is nothing wrong with this. We are essentially good to go. But let's talk about a different scenario. What if we have, or what if we want some form of program that will hold, this program will hold their own funds in the wallet that this program owns. So let's say we want to create some form of game where we will be sending out tokens to our game and the game will lock these tokens, or we have some form of program that will create a crowdfunding campaign and we will ask different users to deposit money in our program to these different crowdfunding campaigns. How do we do that? We obviously need to have some form of way where program can have its addresses, where the program can store different amount of Solana tokens and can do transactions on behalf of that wallet that is owned by the program. So let's say we have this form of scenario. We have a crowdfunding application and the user requests our program to withdraw funds that are stored in the campaign that the user created. That means our program will have some form of withdrawal function, and in this case, user is calling this withdrawal function, and the program is transferring this money stored in that particular campaign back to the user. That means that the program needs to have some form of way how to tell System Program, look, I want to do this transaction, I want to withdraw all this money that I hold in my PDA and transfer it to a user A that called this withdrawal function. So how do we do that? If we take a look at the example that we have previously, which is this one, we're always asking the System Program to do some form of transfer on our behalf, and we need to tell System Program that this is actually us by supplying the private key. This is obviously not possible for programs. Why? PDAs should not have a private key, so we need to have a different signing mechanism. Why we don't want to have a private key stored directly in our program? That means that everyone who will be able to take a look at the source code of our program would be able to know what's the private key for the wallet that for the account that we're interacting in our program. So we need to have a different signing mechanism. So that's where PDAs comes in. Again, PDA wallet is just an account that is derived from our program address, which is our program ID. We actually worked with program ID in our previous lecture where we changed our program ID when we deployed the program. So you can take this program ID and we add some form of seed. So let's say we will call this wallet, for example, Vault. So the address will be generated from our program ID, and that additional seed that we are adding into our into a PDA generation. So it can be essentially anything we can think of to generate some form of random seed. And signing instructions is then executed by using an invoke sign function in our System Program. So that means our program is calling invoke sign function to a System Program, and we supply the seeds of the PDA account or the PDA wallet that we want to subtract. So in our case, we'll call invoke sign to a system program. System program can verify from the actual PDA address if the program owns that particular PDA wallet and execute that transaction on behalf of our program. And we can obviously, as I said before, we can do this invoke sign just by essentially specifying the seeds that we have used to generate our PDAs, and without supplying the private key for our PDA wallet. Because in every scenario, the PDA does not, or the PDA address does not have a private key. So let's just recap this a little. PDA programs wants to be able to sign accounts for cross-program invocation. PDA is Program Derived Address. It is the actual address of our PDA account. On the other hand, PDA account is an account whose address is a PDA. Now, how PDA gets derived? As I said before, the PDA gets derived from our program ID and the array of seeds that we have specifying, and then using SHA-256 function, we are adding it to our program ID and we have a PDA as a result. Now, when we have our PDA, we're also adding bump, or Solana is adding a bump. Why are we adding a bump? PDA needs to be bump of the ecliptic curve because we need to be sure that our PDA have no private key. So essentially, when we are for the whole PDA generation, we're just using program ID, different seeds, we have a PDA, and then we're adding a bump to be sure that we have no private key for our generated address. I hope this is clear to you, just as a brief introduction to a PDA. We will dive a little bit deeper during our hands-on example to know exactly how we can use PDA in our Anchor program. Now let's talk a little bit about Solana program library. So the advantage of the whole concept of the program account, where we have just a program that is, or for example, that we have just an executable account that is storing our program without any data, we have some form of generic implementation that we can use to different forms of input or different forms of input data. So that means that the whole concept of program account model means that we have one generic program that operates on various data. And that this applies also to Solana program library. If you take a look at Solana program library, you can find different generic programs that are included in Solana. So for example, a governance program that will help you create DAOs without any form of implementation, or for example, stake pool, that we can use to easily create different staking pools, or in our case, most importantly, a token program. A token program is something that we have interacted in lesson 1, where we ask token program to create different SPL tokens for us. And we'll be talking a little bit in detail about this in the next slides. So to briefly introduce Solana tokens compared to, for example, Ethereum tokens. On the Ethereum side, we have ERC20 tokens, and that is a token whose smart contract uses a ERC20 standards. All of the tokens on Ethereum, if you want to use the standardized function, are ERC20 standard. If we want to create a token on Ethereum, we can use a smart contract template to create a new token. That means that every token on Ethereum is a separate smart contract. And to create a new token, we need to deploy a ERC20 smart contract on chain. That means that, for example, developers has a little bit more of freedom in creating different tokens on Ethereum, but that also introduced a lot of security issues. On Solana, we're essentially labeling tokens as SPL tokens, and it is a token created with the Solana token program. There is no such a thing as a standard. On Solana, there is a single token program that is already pre-deployed for us, and we already talked about it, how we can interact with SPL token via Solana CLI, but we can obviously interact with that program in any other way that we want to. So to briefly introduce this, we have our token program, which is pre-deployed Solana token program, and we also have a system program. Let's introduce a wallet in this case. This can be our wallet, for example. The owner of this wallet is the system program, but we own private keys for this wallet, so we can essentially ask system programs to do transaction on our behalf. And let's say we want to create a new token on Solana, which we were doing in a lesson number 1. So first, we ask token program to create a mint account. A mint account essentially is an account that has metadata for the token that we are creating. So we can see in the account data that we have some form of mint authority. That means this is, for example, the owner of this token. That can be us. And that person is able to can create new tokens or issue any tokens, burn them, for example, etc. We also specify the supply of our token, which can be, for example, thousands, which is the max supply of our token. And we also specify decimals. This means the decimals that we have after each token issuance. So, for example, let's just say that our wallet that we have created in the previous step is a mint authority for our mint account. So the mint authority is our wallet right here, which is the pub key of our wallet. Now, our wallet can ask mint account to create a token account. So let's say we create a token account, and this token account is then owned by token programs and has an owner. An owner is a wallet or a different wallet that is owning this token account, and this token account is used to store different amount of our tokens. So let's say our wallet will ask the mint account, look, let's create a token account. This token account will be for me, and I will want you to mint some amount of tokens that will be stored in that token account for me. So let's just say mint account then calls mint on the token account, and our wallet is an owner. So now we can see that our wallet is the owner of this token account, and mint account minted some form of amount of tokens into this token account. That results in that our wallet is now holding some amount of the tokens that we have created, but is also a mint authority for this token and can issue or burn different amounts of this token. So now that we have introduced the basics of PDA and also talk a little bit about SPL tokens, let's jump into a hands-on example where we implement a simple Solana program in Anchor framework, and we'll be generating a PDA account for this program so we can store some form of tokens in that PDA wallet and then transfer it out to a different user. Implementing our first Solana program that will be using PDAs. So the process to create a Solana Anchor program is pretty much the same as last week. So let's just start it with Anchor init, and let's call it Solana PDAs. This will initialize a new project for us, and while the project's initializing, let's talk about what we are building today. So essentially we'll be having a really simple demo of how PDAs work, and that will be a simple program for donations. So let's say we'll have three different functions. The first one will be create. This one will initialize a new bank that the other users can call deposit. So essentially, the one wallet creates a new bank, other wallets can deposit into it, and then we will also have a withdraw function that only admin can call. And by calling this withdraw function, all of the money or all of the tokens deposit into our PDA accounts for that particular bank will be withdrawn to the admin or the owner of that bank. So this is pretty much just like a basis app for DeFi. So we'll be creating a PDA. So if a user calls create, it will create a new bank account. This bank account will be a PDA and will be able to hold some form of balance. If the admin or any other user wants to deposit into this bank, he or she will call the deposit function and deposit some form of amount of the tokens that will be going or will be transferred into our PDA that we have created. And we're also adding a withdraw function. This function will still be publicly accessible, but we will have to implement some form of ownership checking inside of it to make sure that only the owner of the bank that we are withdrawing from will be able to withdraw the actual funds. If any other user or any other wallet will try to withdraw funds from our PDA, it will fail. So let's jump into our project. Let's just go ahead into a program that Anchor created for us. And let's remove the initialize function and the account structure or the boilerplate code that Anchor generated for us. And let's just go ahead and start with our create function. This create function will essentially create a new PDA account for our bank. So the process pretty much same as last week. So let's just call it create. We obviously need some context. This context will be called create. And let's just say we need some name for our bank. So this name will be string. And then we also need some return value. In our case will be program result. And now essentially the same situation as last week. Let's just fetch our bank. Sorry. This bank will be mutable and it will be part of our context. So this bank account will be a PDA. And now during the initialization or the creation of the bank, let's just set up a name for our bank, which we have in the function parameters. And we also, since we will be holding some funds in our bank, let's just also keep track of it in one of the fields inside our bank. So let's just say we have bank balance. And we'll be setting up that to 0 right now because we're just initializing the bank account. And as I mentioned before, we need to keep track who's the owner of this bank. So let's just say the bank will have some form of owner. And to get the owner that we want, let's just use the signer's public key. So essentially the one who's calling the create function will also become the owner of the initialized bank account. And we can do it again by accessing our context. In our context accounts, we will have a user, which will be the signer that is calling this function, and we'll use his key as the owner. And now when we're done with that, we also need to return that the execution was successful to Solana runtime, and we are doing that by calling OK. When we're happy with this, let's just go ahead and create our context for the create function. The progress is yet again same as last week, so we're using derive accounts macro to tell that our structure is derived from the accounts. And let's call it create. And now we have our structure, and let's just specify the fields of our structure. So in our case, it will be the bank, which is the most important thing. It will also be our PDA in this case. So bank is just an account of type bank that we will specify later. And we also need the user, which is the signer that is calling our initial or our creation function. So signer. And we also need to reference the system program. So now we have our structure ready, but we need to define some form of macros. So we need to tell that the bank will be the PDA. So we can do it by adding a macro, just like we did last week. We need to initialize our account. We need to specify the payer. That means who will be paying for the account initialization. So we can do user, so that will tell that the person that is calling the create function will also be paying for the creation of our bank account. Let's just also specify the space that our account will allocate. Let's just do 5,000. We'll be talking a little bit in depth in next lectures how to properly calculate space for our accounts, but it's pretty easy. And now, since we're talking about PDA, we need to specify the seeds. I have told you before in our presentation in this lecture that the PDAs are generated from the program ID and some seeds on top. So we can do it by specifying seeds, and the seeds will be an array of different seeds that will be used to generate the PDA's address. And let's just add a string. This one will be called bank account. But this is obviously not enough, because this will create a PDA that with a seed of our program ID and the seed bank account on top. But if we want to create different bank accounts using our program, we'll be running into some issues. So let's just add more seeds into our generation. So we're essentially be making sure that we are generating unique PDAs for each bank account creation. And let's just use, for example, the public key of the signer. So it's the user key as ref. So now we have specified the array for the seeds. The first one is a string bank account, and the other one is the public key of the owner of this bank account. Let's just also add the bump flag. The bump flag, as I told you in the lecture, will make sure that there is no private key for this PDA. It will essentially bump the address of this account off the ecliptic curve. So we'll be making sure that we have no private key accessible for this PDA, and only the actual program can access it. And now that's pretty much everything for our macro. We're good to go, and this will create our PDA. So as you can see, that it is pretty much the same thing as initializing an account in the previous lecture, where we initialize our calculator account. But here we're specifying seats on top, which we are explicitly telling Anchor that we will be creating an account with the public key generated off of this seat and the program ID. And we're also adding a bump on top to make sure there is no private key for our bank account. But we are still not done yet with our create context. We also need to tell that, that our user's account is mutable. And this is pretty much the same thing that we did last week. So yeah, we're essentially set with our create context. We just need to define how the bank will look or how the bank account will look. And that's pretty easy. We've already accessed the bank here, so we already know that we need some form of name, we need some form of balance, and we need to specify the owner of this bank. So we'll probably have just 3 of these fields. So let's just do it right now. Let's just specify that this will be an account. And let's just go ahead and add pub name, which will be the string. We need to add pub balance. That will be unsigned integer, 64-bit integer. And we need the owner that we have specified here. And let's just say it's owner. And make sure that the type of the owner will be the pub key, because we are essentially supplying a pub key to our owner field in our bank account. So now we're pretty much set. We're pretty much set with our create function. Let's just save it up and try to compile our program for the first time if everything checks out. Also make sure that if you're using program result, specify that we'll be using program result on top of your lib.rs. So now when we have created our create function and we have tested that everything compiles just fine, let's go ahead and implement our deposit function. So again, we're calling it deposit, specifying a context for our deposit function. And let's just say we are also adding a parameter that we will call amount, which will be the amount in LAN ports that the user will be donating in our bank. So if you think about it, all that this function needs to do is essentially initialize a transfer from the user's account to our PDA account. So let's just call it transaction. And now we can use anchor lang Solana program system instruction and now we can call a system instruction, which in this case is transfer. The transfer function requires us to specify 3 parameters, which is the input account, the account that we're transferring to, and the amount that we're transferring. So let's just start up with the user's account, which in our case will be context, accounts, user, and yet again we'll be using the user's key, which is the user's public key. And for destination, we'll be using context, accounts, and this time we'll not be using the user's key, but our bank's key, which is our PDA. So let's just type bank and key. The last parameter that we need to supply is the amount that we're transferring to, and we'll just use the amount that is supplied in our function's parameters. So that's amount. So let's just say our transactions is essentially defined using anchor length Solana program. We're calling system instruction that is called transfer. And now just invoke the actual transaction. So let's just type anchor length Solana program invoke. And what we need to do here is to actually specify the transaction that we have created in the previous step, which is TXN. And just like we're used to, we also need to supply the accounts that we will be using for this transaction. So in our case, it will be, again, context, accounts, user, and we'll be using function to account info. This way we have specified that we'll be using the user's account, but we also will be using the actual bank account, which is our PDA. So let's just do that too. So the process is the same, but instead of user, we'll be using the bank account. And again, we'll use to bank to account info. And now we pretty much initialize the transaction. And as I've mentioned before, we're also keeping track of the balance inside our bank account. So when all the transactions went through, we also need to update the balance parameter inside our bank account. So let's just do it real quick here. So let's just do mutable. Context, again, we're using our bank account. And now let's just rewrite our balance attribute. So let's just say balance. And let's use plus equal amount. This will essentially add the amount that the user is donating to an actual balance of our bank account. So we're pretty much set with this one. So let's just call OK. And briefly glaze through what we have implemented here. So we are constructing a function. We're using we are constructing a transaction or transfer using a system instruction transfer from some sort of source account to some sort of destination account. We're also specifying the amount. Now, when we have constructed our transaction, we need to invoke it. We're doing that using Solana program invoke. We're specifying the transaction, and we also, just like we're used to do, need to specify all of the accounts we'll be using for this transaction, which in this case is the user account and the bank account, because those are the only accounts that we are reading or writing from or to. After that, after our transactions complete, we also need to update the balance inside our bank account, which we're doing here. We're using mutable for our balance attribute, and we're adding the amount that the user has donated using this function. After all this complete, we're just letting Solana runtime know that the whole deposit function went through well. Let's just rename our context and just go right ahead and add our context right here. So again, let's just add our derive accounts macro and create our deposit context. So in our case, it will be pretty straightforward for the deposit function. We're essentially need to supply our bank account, and we also need to, again, supply the user and the system program. So let's start with specifying, again, we're using a mutable macro. And the first thing we'll be specifying is the actual bank account. The bank account is type of the bank that we have created before. And when we're all set with our bank, let's just also use the same structure that we have used before, and that's essentially the user, that will be the signer, and also referencing the system program. So we can add it right here, and we're pretty much set with our deposit context. So again, we're specifying, the only thing that we are using in our deposit is our bank account and is the actual signer or the user. So we're supplying it here. Both of these accounts needs to be mutable because we'll be changing them. And we are pretty much good to go with our deposit function. Let's just test it out real quick. Sorry, made a typo here. Be aware that it is not account, it's accounts. And let's just try to compile our program again if everything works out. Okay, seems like we're good. And let's just go right ahead and add our last function, which will be the withdraw function. The withdraw function will be a little bit more complicated because we need to ensure that we have some checks in place that only admin that actually created the bank account will be able to withdraw the funds from our bank account. So let's finish up our program by adding our last function, which will be the opposite of deposit, and that's the withdraw function. The withdraw function should essentially take an amount of money that we want to transfer back to admin of that particular bank from the PDA that is storing the deposits. So let's do function withdraw, and the process pretty much the same as before. Context withdraw. And we also need to specify the amount that we want to withdraw. This is pretty much optional. We can also create the withdraw function to withdraw all of the funds from the PDA. We do have both of these options for a reason, because we're also storing the amount that is stored inside the bank account in our balance parameter. So, but for this purpose, let's add amount, which will be an unsigned 64-bit integer, be a lamp horse that we want to withdraw from our PDA. And again, the return value is program result. And now let's think about what we want to do. The process is pretty much similar with the deposit, but except the transfer is the opposite way, but we also need to add some checks first. So before we do so, we need to access our bank account. So we'll be obviously using our bank account from our context again. And we also need to use we also need to fetch the user account, which is the signer that is calling the withdraw function. So let's just say user. And again, it will be the process pretty much the same. So let's just say mutable, context, accounts, user. which is the signer of the transaction that is calling the withdraw function, we can go ahead and specify our withdraw function, or withdraw context here. So it will be pretty much the same thing as with deposits. Let's just call it withdraw. And we're also, yeah, pretty much the context remains the same for our withdraw function, just like the deposit. You can also, yeah, we can just essentially keep the bank and user account, because this is what we'll be using in our function. So let's just say, yeah, we're accessing bank, we're accessing the user, and now it's time to do some proper checking. So for checking in Solana, we can just do, for example, if statements in Anchor. So let's just say our first check would be if the caller of this function, if the signer is actually the admin of the bank that we want to withdraw. So the check is pretty much straightforward. So let's just say we're comparing our bank owner, and let's just say if the bank's owner is not equal to the user's key, which is the user's pub key, we need to throw some error and stop the execution of our function. We can do that by calling return error and specifying the error code, which, let's just say, will be program error, incorrect program ID. You can obviously specify these errors as much as you want. You can customize them, but this will do for our example. So this is the first ownership check that we are implementing here using a simple if statement. There is also another thing that we need to check. Since we are letting the user specifying the amount that he wants to withdraw, if we want to, let's just say, we need to check if the amount that he's trying to withdraw is actually present in our PDA account. So let's say another if statement. Let's say our bank to account info. And we can call lamports borrow, which will essentially tells us the lamports that are currently stored in our PDA account or in our bank account. And we need to check if that number is, if that amount is less than the amount that the user is trying to withdraw. In this case, we need to throw another error. So yeah, it's pretty much the same thing as before. Let's just throw another error, but it will be a different error. Let's call it insufficient funds. So yeah, we have insufficient funds. So right now what we have achieved is the fact that only the owner of our bank will be able to withdraw or call this function. If it is called by someone who is not the owner of the specified bank, it will throw out the error. And also we need to make sure if it's a right owner and if he's trying to withdraw a more amount that is stored in our PDA, it will throw another error. So that will stop the execution of our function. You may also point out that we're storing the balance as one of the fields inside our bank account. We can use it to check if the amount we are withdrawing is lower than the amount stored, but I'm also using the lamports borrow here to demonstrate that you can use this function to get the amount of the lamports that are currently stored in the specified account. And now when we're done with the checks, the only thing that we need to do is initialize the transaction or the transfer between the PDA and the admin's wallet. What we'll do here is essentially subtracting the LAMP ports from our PDA bank, and we'll be adding these LAMP ports back to the user's account or the admin's account. And we can do it pretty easily. We can, again, take our bank to account info. And just like we access our LAMP ports here, we can call try borrow mutable LAMP ports. Sorry. And just subtract the amount that we want to withdraw. And now we're subtracting the LAMP ports from our bank account, and we need to do the same thing, just the opposite way, to our user that is calling the withdraw function. So we're calling user to account info, try borrow mutable LAMP ports, but we're not subtracting, we're adding the LAMP ports back to our user. These functions obviously only work when there is, because we're trying to borrow the LAMP ports, so we need to be sure that there are enough LAMP ports in our bank account before we are actually borrowing them. And we are making sure by creating this if statement before it, where we are actually making sure that the amount that the user is trying to withdraw is present in our PDA. And after that, we're pretty much done with the execution, and we can tell Solana runtime that the execution went successfully. So let's just, I have a typo here. Let's just check if we are good to go. Okay, so it seems like our program's pretty much fine and compiles fine. So let's just, and also let's just point out, and we have also mentioned it in the previous lecture, that all of the accounts need to store some form of rent to not get pretty much erased or deleted from Solana blockchain. Let's make sure that we will keep enough rent in our PDA so it not gets destroyed. So we can do that by calculating the rent that is necessary to keep our account from rent extension. So let's just say let rent, and we can call rent get minimum balance. And now we need to supply the length of the account where we want to calculate the minimum balance for the rent. So in our case, we'll be supplying our bank account data's length. So let's just say bank. Again, we'll be using to account info. And call data length. And by calling this, we will get the minimum amount of rent that we need to keep stored in our PDA accounts for it not to get destroyed, because we're essentially enabling the admin of our bank account to withdraw any specific amount of funds from the bank account. We need to make sure that even after the admin withdraws the money from the bank account, the bank account still needs to keep enough LAMP ports to pay for his rent. And let's just add it to our LAMP ports borrow, add rent to it. And now we are pretty much sure if we do this, let's just try if it works out. Yeah, and now we're sure that we can only withdraw the amount of money so there is enough rent kept in our PDA to not get it destroyed. But this is obviously up to your implementation, because if we, for example, want to make a withdraw function where the withdraw automatically withdraws all of the funds that are stored in the PDA, we can then pretty much get all of the funds from our PDA and close these accounts if we don't want to use them anymore. But in this case, the admin can withdraw any funds he wants and still keep his bank running. So essentially he can withdraw just 2 SOL, keep 2 SOL in his bank, and other users can still deposit money into his bank. So this is a little bit more flexible. Yeah, so now we're pretty much done with all of the 3 functions that we needed. We have withdraw, deposit, and creation of the bank. So we have pretty much a standard app that represents the DeFi or pretty much the simplest example of a DeFi on Solana. Thank you for attending today's lecture, and now I will hand it over to my colleague to give you details about our next assignment.
Hello everyone. Today you have learned about PDAs, which is an essential concept used on Solana. And with the knowledge that you have learned until now, you can already create a lot of useful programs. For the next task assignment, you will be programming Twitter functionality where users can create new tweets and others can add reactions to the tweets. And as usual, we will share the GitHub Classroom link on Discord. In the next lecture, I will give you some development best practices tips, and I will also show you a few hands-on examples how you can debug and test your programs. So thank you for today, and see you next time.